So, we consider now the next sub problem, namely floor planning. So, floor planning, let us first see what this problem is all about. Now, see, in typical VLSI physical design, what we are trying to do? We have our playground, which is the silicon floor, where we have to lay out all the circuit components. Floor planning means, just to recall the analogy I gave earlier, it is like building the plan of a house. So, I have my circuit blocks, I have to make a planning where to put which circuit blocks on my silicon floor. So, once I do this planning in a nice way, the task of laying out and handling the physical design process in subsequent stages becomes much easier, because one thing to remember, in physical design we are tackling circuits or netlist containing millions of components. So, once we do this kind of partitioning, floor planning, we are going for something like a divide and conquer approach. We are reducing the complexity of the problem to a great extent by dividing or splitting the problem into simpler sub problems and then handling them just one by one independently. So, you can say floor planning concerns finding the approximate locations of the modules on the layout surface. Now, some assumptions are typically made. The available region, for example, the silicon floor is considered rectangular in shapes. The modules that you are trying to place, they are also typically considered to be rectangular, but sometimes you can have other module shapes like L shaped modules. We shall see these later. Okay. So, let us look at a diagram which will just apprise you about the overall scope of the problem that we are talking about. On the left, we show some modules that we are trying to place, and this rectangular region on the right is our silicon floor. So, these 5 blocks we place like this: block A, B, C, D, E. These are our tentative floor plan. Now, there is another thing which we are also showing here, which may or may not be done in the floor planning stage. Now, in fact, in our lecture sequence, we shall be considering this sub problem later. Like, in addition to creating the floor plan, we are also tentatively fixing up the position of the external pins or the I/O pads. These are the positions from where our external connections will go out, okay? And also the power supply lines. This solid edge indicates the ground line, this dotted edge indicates the power supply line VDD. So, as you can see, this is the norm actually. Ground and VDD lines are typically laid out on the same layer, metal layer. So, these ground and VDD, these two nets are not intersecting each other, you can see. So, this is a typical solution to the floor planning problem, including power and ground planning. Okay. This is the overall chip planning I am showing, but if we do not consider VDD and ground planning here, our floor plan will only consist of the blocks and their relative positions in the floor. Okay. We shall see some examples later also. So, the problem definition goes like this. Suppose we have n number of blocks whose areas are given, and there is another thing, some of these blocks can be fixed, some of these blocks can be flexible. Fixed means I know the width and the height of the blocks, but there are some other blocks I know how many gates or transistors are there, which means I know the area, but my height and width is still flexible. So, I can adjust that. So, my area is given, okay. Those are called flexible blocks. So, and we can have some bounds on the aspect ratio. Aspect ratio means height divided by width. So, I mean, ideally speaking, I would like a block to be square in shape, but it can be thin, either vertically aligned or horizontally aligned, but how thin, that aspect ratio you can possibly specify as a constraint, that it cannot be thinner than this, the height to width ratio cannot be more than or less than this. Okay. So, the output will be the exact location of each block, their widths and heights. Well, for the fixed blocks, width and heights are already known. For the flexible blocks, you will have to fix up. Their product will be equal to their area, and of course, they will be lying within the limits or the bounds of the aspect ratio Ri and Si. The objective of will be of course to minimize the total layout area, and also for the critical wires or the critical nets to reduce the wire length. But one thing you remember here, although we are talking about reducing wire length, we are only talking about a tentative placement of the blocks. So, exact wiring of the wires we have not done yet. We can only make a very coarse estimate at this stage. So, even with that rough estimate, we can say that, well, my critical net is becoming too long, let us bring these two blocks together, keep them side by side, something like that. Okay. Fine. Now, one thing, we shall be talking about the placement problem later. Floor planning and placement are quite similar, but there are some precise differences also. Let us see what the differences are. Now, in floor planning, as I said, some of the blocks may be flexible in nature, in the sense that their area is known, but their heights and widths are not yet decided. And also in each block, the pins are there, like for example, suppose I have a fixed block like this. So, let us say this corresponds to a NAND gate, let us say. So, my two inputs can be here and here, my output can be here, these are fixed pin locations. But if I have a flexible block where I know that there are 6 pins I need, but their exact locations are not fixed, they can move around. Okay. The pin locations are also flexible here. So, in floor planning, the exact location of pins, they also may not be fixed, you also need to fix the position of the pins. But in the placement problem, we assume that all the blocks have well defined geometrical shapes and also their pin locations are fixed. And although in floor planning we do not keep space for interconnections, but in placement we explicitly keep space for interconnections. Like an example, now in floor planning I can say that I have 3 blocks A, B and C, which has to be placed like this, B on top of C and A to the left of B and C. But in placement, here I will specify it like this, this is my block A, this is my block B, this is my block C, and there is some space in between I have kept for interconnections. This is the output of the placement problem, right. So, this is the main difference between floor planning and placement. And the point to note is that the floor planning problem is more difficult to handle because you have the concept of flexible blocks. So, you have the area given for a block. So, there can be so many different possible shapes of the block, you will have to find out which particular shape can give a more compact and a better layout. Okay. So, this is not an easy problem, but in placement, because the shapes and sizes of all the blocks are fixed, the problem is much easier. But in floor planning, in addition to placing them, you also have to find out the aspect ratio of the blocks, the exact shapes of the blocks that are flexible, right. But we shall see in some of the design styles, the two problems are not different, they are the same. Okay. So, let us take one example floor planning problem. So, we consider that there are 5 modules, width and heights are given. So, these are all fixed modules, none of them are flexible. So, A is a square module 1 by 1, B is 1 by 3, C is 1 by 1, D is 1 by 2 and E is 2 by 1. These are 3 possible floor plans. Now, one thing you see although I know that B is 1 by 3, but I can lay it out either vertically or horizontally, that flexibility I have. Okay. Similarly, D, I can lay it out either horizontally or vertically, because I know the shape of the block, but there is no problem if I rotate it by 90 degrees. So, a horizontal block I make it vertical by rotating, that flexibility I have. So, by doing that, these 5 blocks can be placed in several ways. So, you can have several alternate floor plans. So, the point arises here is that, so once you have many floor plans for a given problem, you should have a mechanism to determine which of these is better than the other. You will have to choose the best floor plan among all the alternatives. Okay? This is something we have to do. Now, coming to the design style specific issues, let us have a quick look at this. For the full custom design style, you recall in the full custom design style, the blocks can have any arbitrary shapes and sizes. They can be small, they can be big, they can be square, they can be rectangular. So, both floor planning and placement problems will come into the picture for the full custom design style, and here you need all the steps that are required. But for standard cell, the dimension of all these cells are fixed, because you know the cells are picked from a library, and as I said, the heights of the cells are fixed, but the widths can be different. But once you choose a cell, the shape and size is fixed and it has to be placed in this way only. You can you are not also allowed to rotate these cells in a standard cell layout. So, for standard cell, floor planning and placement problems are the same, they are not different sub problems. So, when you have a large netlist, you go through 2 steps. First, you do a global partitioning, you partition the whole netlist into smaller pieces, and each of the piece you possibly map into individual regions, maybe one row of the standard cell. You lay them out into one row of the standard cell and carry out the placement. Similarly, for gate arrays, you have so many gates which are spread on the layout floor, there are so many gates. So, when you say floor planning, you are planning where to place the gates. When you talk about placements, you are talking about the same thing, how to place the gates. So, floor planning and placement even for a gate array is identical, they are not different. So, these 2 problems are the same. Now, I had said that when you have a number of alternate floor plans to compare, you should be able to just evaluate them with respect to some cost. So, let us see how we can evaluate the cost. So, this is required, as I had said, that the number of feasible solutions of our floor planning problem can be very large, and determining the best solution this has been proved to be computationally complex, NP hard. Now, when you compare more than one floor plans, there are several ways in which you can make this comparison. You can look at the total area, you can look at the total wire length, you can evaluate how easy or how difficult will be interconnect the blocks, how interconnection complexity is different. Like for example, you may place in the floor plan 2 blocks which are little far away, but the number of connections are pretty large between them. So, you can say that your interconnection complexity will be larger there. Okay. Minimize delays for the critical paths. So, you see that how far they are, the points you want to connect, or any combination of these. Okay. Determining area is not difficult, because you see your total silicon floor is rectangular in nature. So, if you can have a better floor plan, your that size of the rectangle will reduce. So, just height multiplied by width will be your area. So, you can measure the size of your area very easily by looking at the width and the height of the total overall floor plan and taking the product. Okay. So, area can be easily estimated. So, for each candidate floor plan you can measure the area very easily. Okay. But wire length. So, I had said at this stage you are only allowed to make a very rough estimate, because here at this stage you have not even kept separate spaces for interconnection. You do not know how the wires will be laid out, you can only make an approximation. So, one popular method which is used is that I am just explaining with the help of this example. Suppose I have 3 blocks shown by these 3 rectangles. So, what I here I assume is that in each of these blocks there can be several pins which need to be connected to several other pins in the other 2 blocks. So, we assume that all the pins are merged and residing at the centers of the blocks. Suppose these are the block centers, I assume that the pins are residing at the centers of the blocks, and I calculate how many interconnection lines are there between this block and this block, that is Cij, between block I and block j how many interconnections are there, and Dij is the distance. Distance I am calculating as the Manhattan distance. So, what is Manhattan distance? Suppose I want to connect a point this with this, Manhattan distance means you go vertically, then you go horizontally. So, this y plus x, Manhattan distance is this x plus y. So, you can easily calculate the Manhattan distance given the coordinates of these points, number of interconnection wires you know. So, in this way you can have a very coarse estimate across every pairs of blocks. You see how many connections are there multiplied by the Manhattan distance between the 2 blocks. This will be a very rough estimate of the wiring length, total wiring length. Now, the total cost you can estimate as some weighted sum of the area and the weighted length. Now, it depends, in some cases your area may be more important, you may give higher weightage to W1, but if your interconnection length minimization is more important, you can give a higher length to W2, higher weight. So, this W1 and W2 can be specified by the user. Now, there is another way to estimate the goodness of a floor plan. This is by measuring the dead space. Dead space means the space within a floor plan which is wasted. Like you know, the total area of this floor plan you can estimate by multiplying the height by the width, and the individual blocks are there. So, you take the sum total of the areas of the blocks. So, you get the areas of the blocks. If you subtract that from A, you get the area of the so called unoccupied space, which is sometimes called dead space. So, that divide by A, if you calculate the percentage, this sometimes we call it as dead space percentage. Sometimes instead of area we can say that we want to minimize the dead space percentage. Reducing dead space percentage means you are reducing the area, it means the same. Okay. So, the problems are similar. Now, let us see how we can represent a floor plan. Slicing structure is a very common way of doing that. Let us try to see what it is. Slicing structure means it is like a rectangular dissection. Like let us say, suppose I have a floor plan, say there are many blocks. Dissection means I can cut the floor plan either by a vertical line or by a horizontal line like this. I can cut it into two parts. These are called dissections. So, once I do a dissection, I divide the floor plan into two smaller floor plans, right. So, slicing structure actually tells you how to slice a floor plan repeatedly until you get the basic blocks. So, that slicing tree is something which specifies that slicing structure. I shall show some examples. Slicing tree is nothing but a binary tree. At every stage you are doing one slice, a horizontal slice or a vertical slice. In this binary tree, the vertex or a node represents either a vertical cut represented by V or a horizontal cut represented by H. Later on we will see that a third kind of vertex can also be there called a wheel, which appears for some floor plans which cannot be sliced. This we shall see a little later. And the leaf of the tree indicates a basic block, the blocks that you want to place in the floor plan. Let us take an example. Suppose I have a floor plan like this, A, B, C, D, E, F. There are 6 blocks which are placed on the floor like this. Now, this tree on the left represents one possible slicing tree. Let us see how it is done. Let us start from the leaf side. E, F connected by a vertex V, which means E and F are partitioned by a vertical line. This whole thing indicates this entire rectangle E, F. D and this entire rectangle is connected by a horizontal line. D and this entire rectangle is connected by a horizontal line, this one. This whole thing and C is connected by another horizontal line. This whole thing and C is connected by another horizontal line. And on the other side, AB is connected by a horizontal line, AB by a horizontal line. This whole thing and this whole thing connected by a vertical line, this vertical line. Okay. So, this floor plan can be represented by a slicing tree like this. You can check, this is also a slicing tree which represents the same floor plan. So, this C and D are actually interchanged, because you can see there are two horizontal slices. So, either you do this slice first or this slice first, does not matter. So, either you do this D first and then C, or C first and then D, does not matter. So, for a given floor plan, there can be more than one slicing trees possible. Okay. Fine. Now, a slicing tree can be represented in a compact way by a something called a Polish expression, also known as a postfix expression. Now, what is a Polish expression? We shall explain it later, but here let me just briefly tell you about. When you have a node like this, let us say V, where you have E and F. In the Polish notation, we express it as, first we write the leaf 2 blocks followed by the root V. Suppose I have another this H here, this connects here, and I have another block A connected here. Then I will write A and this whole thing represents this whole thing, H after this, A whole thing H. So, this is the basic idea behind writing a Polish expression. So, when you have any tree like this, you can write down the equivalent Polish expression. I will show you this. Well, V I am showing here by a vertical line and H I am showing by a by horizontal line, AB horizontal line, AB horizontal line. Here on the other side, EF vertical line, you see EF followed by a vertical line, D this thing followed by horizontal line, D this thing followed by horizontal line, C this whole thing followed by horizontal line, C this whole thing followed by horizontal line, this whole thing vertical line. So, this we shall again explain later, but this is how you can express a layout in the Polish notation, right. Now, this is an example of a floor plan. You can see here also we have some blocks which are very nicely placed, but you cannot slice them. As you can see, you cannot have a continuous vertical or a horizontal slice that can partition this floor plan. This is something which is called a non-sliceable floor plan, and a topology like this, 5 blocks which are oriented in this fashion, this is called a wheel. Okay. So, a wheel in a floor plan is represented by a vertex with 5 child nodes. Like you say, this is represents a wheel in this floor plan, D, C, F, E, G, C, D, E, F, G. So, C, D, E, F, G represent a wheel, but once you define it as a wheel, the rest can be sliced. You can have a slice here, you can have a slice here, and you can slice this and this. Okay. So, you can have AB, you can have a slice vertical, this and this you can have a vertical slice, then you can have horizontal slice, horizontal slice. So, you can have a, this is a composite tree which consists of horizontal and vertical slices as well as this wheel. Okay. Right. And lastly, I shall look at another representation of a floor plan which is also a graph representation. So, here the floor plan is represented by not one but 2 graphs. Directed acyclic graph means that the edges have some arrows. So, one of the graph is called horizontal polar graph, other is called vertical polar graph. So, for the horizontal polar graph, for example, a vertex will represent a vertical channel, and edge will indicate that the 2 channels are on 2 opposite sides of a block, and edge weight will indicate the width of the block. Okay. So, let us take an example to explain this. Let us take this example. So, this is a layout or a floor plan. This is the horizontal polar graph. In the horizontal direction, you see these are the vertices. What does the vertices indicate? The vertices will indicate in each place where you have a vertical line. Here I have a vertical line here, next I have a vertical line here in this block, here I have a vertical line here in this block, here I have a vertical line here, and at the end I have a vertical line here. Similarly, in the other direction I can have a vertical polar graph where I look at the horizontal lines. I have one horizontal line here, one here, one here, one here, and one this whole thing. And these weights, like the weight, like see this and this, they are connected by an edge. This edge and this edge are connected by a block, and the height of the block, that will be the weight of this edge. This node and this node, this is the block in between. So, the height of this block will be the weight of this edge. This and this, the height of this block will be the weight of this. Similarly, in this direction, this and this, the whole line is there. Okay. So, this will be the weight, the whole width. So, these 2 graphs, you can check that if you are given these 2 graphs, from these 2 graphs you can reconstruct this floor plan. Okay. So, this is also one way to construct the polar graph. Now, next we shall be seeing some of the floor planning algorithms, how floor planning can actually be carried out. Okay. So, just we end this lecture 8 now. So, in our next lecture we shall be looking at the algorithms for floor planning. Thank you.